Okay, so these are, I gotta do it for the camera because I forgot. Okay, so these are number 10, unit 7, day 2. This is a PowerPoint that I mistakenly gave you during the hurricane days, and I said, keep these, we're gonna go back to them. So now we're back to them. Okay, so lone pair versus bonding pair. Lone pair are the electrons that are not participating in the chemical bond. Your bonding pair are the ones that are participating in the chemical bond. But your lone pair of electrons are going to influence the shape of your compound, which we will look at the end. All right. So, okay, so 2 things that we need to learn about today. One is how do we determine if something is polar versus nonpolar? And then 2, we need to learn about the different shapes of our compounds and what they look like and what they're called. So let's first talk about how do we determine if something is polar versus nonpolar. So in order to figure out if something is polar or nonpolar, what you can do is you can draw your Lewis dot structures for your compound as a whole, and then you can look at your distribution of electrons. So your lone pair of electrons are going to be represented by the dots that are left over once you draw your Lewis dot structure for your compound as a whole. Okay, and you're going to look at where are those located, and that's going to tell you if it's polar or nonpolar. So, for our example, we have BeCl2, which is beryllium chloride. Beryllium chloride, it has 1 beryllium in the middle, surrounded by 2 chlorines on each side. So we have 1 chlorine, its Lewis dot structure looks like that. We have 1 beryllium, Lewis dot structure looks like that. And then we have another chlorine where the Lewis dot structure looks like that. So when that makes a bond, your 2 electrons in the middle, so these 2 and these 2, are going to come together to make your bonding pairs. And then all of your other electrons are going to be known as your lone pairs. So your Lewis dot structure for your entire compound is going to look like this. So we have this compound, and we have to determine, is it polar or is it nonpolar? So polar okay, so these 2 single bonds, remember these are single bonds, so the single dashes represent single bonds. These 2 are your bonding pairs. All the other dots represent lone pairs. So to determine if something is polar or nonpolar, you have to look at your dots and look at where they are and see if you have an equal distribution of electrons or an unequal distribution of electrons. So if you have a polar substance, that means that you have different charges on either side of your compound. If you have a nonpolar substance, that means you have the same charges on either side of your compound. So if we look at beryllium chloride, we can see that on either side, our chlorines all have dots around them. Those dots represent valence electrons. Electrons have negative charges. So anytime we see dots, we need to see negative charges. So I drew a negative charge here, showing that these electrons all are going to have a negative charge. And then I drew another negative sign here, saying or showing that these electrons also have a negative charge. So if you have a negative and a negative on either side of your compound, you're going to have a what? Polar or nonpolar? Is this polar or nonpolar? This is nonpolar because you have the same charge on either side of your compound. Okay? So a nonpolar substance, an example of that is going to be our beryllium chloride, because we have dots all over our substance, all over our compound, which means we have the same sign on both sides of our compound, which means we have a nonpolar compound. Okay? So that is what you're going to do when you are determining if something is polar or nonpolar. You're going to draw the Lewis dot structure for the compound as a whole, and then you're going to see, do you have the same sign on both sides, or do you have the different sign on each side? And that's it. Okay. Now, the same sign, it can either be two negatives or it can be two positives. If it's the same sign, whether it's negative or positive, then it's going to be nonpolar. Okay? So beryllium chloride is nonpolar. And then, I think we already talked about single, double, triple bonds, but just to review, single bonds are represented by two shared electrons. So that is our single dash. Our double bonds are represented, our double bonds are 4 electrons shared, and it looks like 2 dashes. And then our triple bonds are 3 pairs, and they make 3 dashes. Yes, sir?
Didn't we already do this?
Yes. It's just a little review.
I'm trying not to take the notes.
If you already have it in your notes, then no, you don't
Oh,
need to
no, I
rewrite it.
don't.
Okay. If you
So I should be writing
if you don't have it in your notes, then yes. If you do already have it in your notes, then you don't need to rewrite it. Okay. So single bond is 2 electrons, double bond is 4 electrons, triple bond is 6 electrons. Okay? Who can tell me which one of these is the strongest? Which one of these is the strongest?
Okay, better answer this.
Triple bond.
No,
Single bond.
What,
is it the triple?
It's triple.
It's the
what
double.
were you gonna say? Colin? Triple? What were you gonna say? What'd you say?
Me?
Louis?
Oh yeah, double.
Oh, double?
The double's the middle one, right?
Well, it wasn't 1 or 3, was it now?
Look, you got a 50% chance. I'm going.
Oh, for real?
I'm going triple.
So your triple bond is your strongest bond. Your single bond is your weakest bond. And the double bond, since it's in the middle, is moderately strong. So your triple bond is your strongest. Can someone tell me why our triple bond is our
Because there's
strongest?
3 lines instead of 2 or 1.
Because there's 3 bonded pairs, so there's 6 electrons altogether. So it's going to take a lot of energy to break all of those bonds. Yes. All right. Okay. Okay. So don't write any of this down. Listen to what I'm going to say. So there's 2 ways that you can figure out if something is polar or nonpolar. One of them being you can look at the electronegativity of all the atoms, and you can look at which one is more electronegative, and then there's a chart with a bunch of numbers, and you can look at the chart and like figure it out. So what we're going to do is, or what I think is easier, because the chart of the numbers is not given to you, you have to memorize that. So what I think is easier is just this. If you draw the Lewis dot structure, and if you look and see where are your signs, then you can look and see if it's polar or nonpolar. If you have the same sign, then it's nonpolar. If you have different signs, then it's polar. That's all you have to do. So, I'm not going to go over all that. Okay, this word, dipole. So dipole, our prefix di means 2, and a pole is like the north and south pole. You have 2 ends of something. So your ends, or your poles, are the 2 ends of your compound. So going back to our beryllium chloride, each of these chlorines is a different pole of our compound. So our dipole, we have 2 poles. So this pole is our negative dipole, and this pole is also our negative dipole. I know, I draw mine like 8s, but it needs to look like that. As long as however best you can draw this, okay? That's what mine it looks like. That's fine, okay? So it's just the end of the compound. So this end of the compound is negative, so it's a negative dipole. This end of the compound is also negative, so it's also a negative dipole. You can either have a negative dipole or a positive dipole. It's just the end of your compound. That's all it is. Okay? So that's what dipole is. Okay, so now let's look at a polar substance. So water is a great example of a polar compound, and next semester we will have a whole unit on the unique properties of water because it is polar. So looking at our water molecule, we have oxygen in the middle. So oxygen has 6, so 1, 2, 3, 4, 5, 6. And then it has 2 hydrogens that also have 2 electrons. So this is going to be 1 bond. and this is going to be another bond. So your water looks like that, okay? And you have these two lone pair of electrons. Now, those lone pair of electrons, what you'll see your water molecule most look like is you'll see it drawn like this. So that is what our water molecules look like, okay? So now we need to see, drawing the Lewis dot structure, so that's our Lewis dot structure. Now we need to see, is it polar or nonpolar? So I have these dots up here. Our dots have what kind of sign? A negative or a positive? A negative sign. So this is our negative dipole. Each one of these is a negative dipole. So dots represent electrons. Electrons have negative signs. So these are our negative dipoles. Hydrogens, do you see any dots on these hydrogens? No, so what sign is going to be attached to these hydrogens? So these are your positive dipoles. Probably should not draw eights. They literally look like eights.
Don't connect the top piece.
I know.
There.
There we go.
That's about 8.
You're an 8.
Oh.
Nah, I'm 10.
There we go.
See.
Okay, so these are your negatives up here, right? And then these are your positives down here. Okay, so if you have your negatives up here, if you have a negative on one side and positive on the other side, you have a polar substance. So, yes.
Don't suck my shoe.
Okay. Are we okay now?
It looks like a sad
Is it
face.
okay?
Oh, yeah.
Well, it looks like a sad face.
The thing. They just drew it. It looks like a
So
sad
that-
face.
I'm just like, go back here and you see the
Oh,
sad
yeah,
face.
you see it like the circle thing.
The eyes and the nose and it's just like.
Miss Mike, can I go to the bathroom now?
Sure.
I got you, Miss Mike.
It looks like a water molecule to me, but
Yeah.
okay.
Look, you gotta look in
Looks like a sad face.
You got the eye, you got nose.
Oh, I see it now.
Two eyes.
Go stand back there.
No, okay. I believe you. I trust you. Okay. So this is your polar. Go. So this one is your polar molecule and this one is your nonpolar molecule. This is polar because you have negatives and positives. You have each sign on opposite sides of your molecule. This is nonpolar because you have the same sign on opposite ends of the molecule. Does that make sense? Different signs on different sides, same signs on different sides. Yes? Yes? Okay, we'll do more examples later, but for right now, does that make sense? Does anyone have any questions on how to determine if something is polar or nonpolar? Okay, I'm gonna move on. Did you need something?
Me?
Yes, you.
I got one stuff to look at.
Okay, why don't you go back to class? For right now.
I suppose.
Thank you. This one we don't need to know. That one. So properties of covalent compounds. We already talked about the differences between covalent and ionic. So you should already have this in like your other notes.
Yeah.
I think for unit 7, day 1, number 5. Okay, so these we already have those. Okay. So these, is this ionic or covalent?
That is,
Guys, is this ionic or covalent? This should take you 2 seconds.
Oh, covalent.
It is ionic. This is lithium. Lithium is a metal. Chlorine is a nonmetal. If you have a metal and a nonmetal, it is ionic. Ionics are always going to be polar. Always and forever. So what you're going to have to do is, if I give you a compound, you're going to have to tell me, is it ionic, is it covalent nonpolar, or is it covalent polar? So ionic bonds are always going to be polar because you're always going to have different signs on different sides. So lithium is going to be your positive, right? Because it's a metal, so it makes a cation. Chlorine makes an anion. You will always have a negative and a positive on opposite ends. So your ionic bonds are always polar. So you should never have a non-polar ionic. That doesn't work. Okay? H2O, what is that? Covalent. And then what is Cl2?
Oh, that is.
That is also covalent. Now, with covalent bonds, your covalent ones are the ones that can either be polar or non-polar. So your covalent bonds you're going to have to draw them out and figure out, do you have the same signs or do you have different signs? So for H2O, I have it drawn here. What did we say water was? So water will always be polar covalent. And now we need to figure out, is Cl2 polar or non-polar? So if we have two chlorines, chlorine has 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So that's going to make that. Okay? So if I have this, do I have a polar substance or a non-polar substance?
I'd say no.
This is a non-polar substance because you have a bunch of dots here and you have a bunch of dots here. Anytime you see a dot, or anytime you see dots, that is going to be a negative sign. So because you have negative signs on either side of your compound, that is going to make a non-polar substance. Yes, Bailey?
Can you just like explain the pause, like where you write negative and positive, like to know what charge it is?
So if you see dots, those dots represent electrons. Electrons have negative charges. So anytime you see dots anywhere in your Lewis dot structure, it will always have a negative charge attached to it. So because we have dots here and here, I have negative signs.
So basically, if there's like little subscripts, it's covalent.
No.
Why?
Because you can have subscripts in an ionic. You can have subscripts in an ionic bond.
Alright. Keep going.
Yes, Colin.
So it can only be covalent and polar if it has hydrogen in it? Can it only be polar, covalent and polar if it has hydrogen in it? Because that's the only gas that doesn't have.
I'd have to look into that. Because I don't know if it's a coincidence or if the hydrogen makes it polar. That's a good question. I'd have to look into that. Because most of the time, so most of your covalent bonds are going to be non-polar. Water is weird in that it is a polar covalent substance. So if it's a polar covalent, that's an exception basically. Most of your covalent compounds are going to be non-polar. You have a few that are polar, water being one of them. So yeah, I'll have to look into that if it's because it has hydrogen or not. Yes, Tanner.
So does that mean that we can only consume like the polar stuff? Because we can only drink like water, but we can't drink chlorine because it's non-polar.
You can drink it, you just won't survive.
That's what I'm saying. Like you can only drink the polar.
I
So
can survive it.
you have inside of your body, you have a lot of ionic substances, a lot of ionic compounds. In order to dissolve those ionic compounds, you have to dissolve it in a polar substance, and water is a polar substance. So it's just that water is it's your universal solvent, so it's just easier to dissolve all the things that you need dissolved. So that's why. I don't necessarily think it's not just the polarity of it, it's a lot of things, but yeah. Okay, so does everyone understand, again guys, seriously, serious time right now. Does everyone understand how this is polar and this is non-polar?
Yes.
Do we see why this is polar? Because there's a negative and a positive on opposite sides. Does everyone see why this is non-polar? Because you have the same sign on each side. Real talk, does everyone understand that? Okay, we will do more practice before your test, but while I have you here, I just want to make sure everyone's good. Okay. So, yes, good job. All right, so now look at these and take a few minutes to look at these and tell me, are these ionic, are these polar covalent, or are these non-polar covalent? So, go. So this is what you're gonna have to do on your test. You're gonna have to look at a compound and tell me, is it ionic, or is it polar covalent, or is it non-polar covalent?
Wait, you said ionic is always polar?
Mm-hmm. So you will never have to specify as if ionic is polar or non-polar, because ionic will always be polar.
Oh my god, I feel so stupid. Like, I really asked that question earlier? Okay.
What?
Like, I completely forgot what covalent and ionic bonds were, but that's literally what we just had the 2 quizzes on. And
Yeah.
I'm like, oh, I thought you did something that I completely missed while I was out.
No.
But it's alright. I understand everything now.
Good.
No,
It's all that matters. Yes, ma'am.
Can I go back?
Those make a covalent bond, right? And then you gotta see by the electricity. You said, oh, this is good. And then you gotta see that you can little dot in the carbons and the other thing. So you do 1, 2, 3, 4, like that.
Wait, yeah, right? The oxidation numbers is the amount of dots that you put on?
And then
That's what,
no, not the oxidation number, the
electrons, how many?
Number of valence electrons.
Yeah, how
But
many
then
is
there's
each
like 6
element?
and 4, and like they aren't so there's a positive and a positive on the other side. That doesn't make it polar, so it's not polar. So the first one is non-polar covalent, and then the next one's ionic.
Did you say positive, Tanner?
Non-polar covalent.
Right, but did you say it's non-polar because they're both positive?
No, I said it's non-polar because it's like the positive and the negative. No?
I'm kinda confused.
Alright, so first of all, tell me if it's ionic or if it's covalent. So number 1, ionic or covalent?
Ionic. Ionic.
Covalent. So,
That was gross.
so covalent, guys. Covalent is if they're both on the right-hand side. You have 2 nonmetals. So carbon and oxygen are both on the right-hand side of the periodic table. If you have something from the left-hand side, so column 1 or 2, and then, or your transition, if you have one of those, and then the other thing is on the right-hand side, so one of each, that is when you have ionic. So CO2 is covalent. What is MgO?
Ionic.
That one is ionic. So magnesium is ionic. It's in column 2. It's a metal. Fe2O3, ionic because iron is a metal. What about N2? Covalent. What about P2O3?
That is covalent.
Covalent. What is the name of this? How do you name P2O3?
Diphosphorus trioxide.
We don't need liquid.
What is CaCl2?
That is covalent.
That is ionic.
Damn.
Ca is calcium. It is in column 2. It is a metal. And then what about Br2? Covalent.
Atom.
Good shit, baby.
And it is diatomic. So your diatomic molecules are always going to be covalent. Yes. Okay. So for your ionic ones, those are always going to be polar. So these are all polar. So now we need to figure out for these covalent ones, are they polar or nonpolar? So our first one, we have carbon dioxide. What do you think? Polar or nonpolar?
Non-polar.
You think it's nonpolar? Well, so you have carbon in the middle, and it has 4 valence electrons, and you have 2 oxygens on each side that have 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then these electrons are going to go inside, and then these electrons are going to go inside. So it looks like this with these 2. Okay? So if you have dots here and dots here, that means you have a negative sign. And honestly, you could draw a negative sign every time you see dots. So those dots are going to have a negative sign. Those dots are going to have a negative sign. These dots are going to have a negative sign. And those dots are going to have a negative sign. So do you have different signs?
No.
Or do you have the same sign?
Yeah.
If you have the same sign, what do you have? Non-polar. So yes, this is non-polar. Good job. All right. What about nitrogen? What do you think nitrogen? Polar or non-polar?
Non-polar.
So let's look. So nitrogen has 5. What's going to happen is that these are going to form a bond, these are going to form a bond, and then these are going to form a bond. So nitrogen makes a triple bond. And then you have 2 lone pairs on each, or a lone pair on each side. So you have dots here and dots here. So you have what sign here? You have a negative sign here, and what sign here? Negative. Do you have different signs, or do you have the same sign? If you have the same sign, what do you have?
Non-polar.
So yes, your nitrogen is non-polar.
Wait, can you explain how you get different signs? Like, how do you get different signs in each of those little circles? Like, what's different from the top one and the bottom? That makes it. Oh, I mean, they're still negative, but.
They're both non-polar.
Oh.
Ionic is always polar. So ionic, so if we have MgO, Mg is 2, and oxygen is 1, 2, 3, 4, 5, 6. I think this should be MgO2.
Ooh, I'm right.
Or no, Mg2. Yeah, this should be, hold on. I don't know. Anyway, okay, Louis.
Yeah.
Mg is a metal, so
Yeah.
it's going to form a cation. Oxygen is a non-metal, so it's going to form an anion.
Yeah.
So because you have a positive and negative, because you have different signs on either side, you have a polar.
Oh, okay.
And for ionic, it will always be that. So your metal will always be positive, your non-metal will always be negative. So you're always going to have opposite signs on opposite sides.
Okay.
So ionic will always be polar.
Alright.
It's your covalence that you're going to have to
Alright.
figure out. P2O3, don't worry about that one. BR. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this one is going to be your single bond. So bromine, is it polar or non-polar?
Non-polar.
It's non-polar because you have a bunch of dots here, so that's negative. You have a bunch of dots here, so that's negative. If you have the same sign on either side, you have what?
Non-polar.
Non-polar. I said don't worry about P2O3 because it's too complicated. They won't give you that, so I'm not going to give you that. I'm not going to expect you to do that. It's too
Isn't that one all for nothing?
Well, it's non-polar. Did you say non-polar?
Yeah.
Good job.
Oh, what if she didn't?
Yes. But they're not going to give you. I'm not going to give you one that's big. That big. That's too big. Okay. Okay. So let's move on to our shapes. Okay. So for your lab tomorrow, listen. Your lab tomorrow, what you're gonna have to do is you're gonna have to use the shapes that I go over today. You are going to be building those shapes using marshmallows.
Oh,
Dip-
hey, can we eat some?
So you are going to be building those shapes using marshmallows, and then once I'm not done with the notes, guys, get your notebooks back out. So once you have built your shapes using your marshmallows and your toothpicks, then yes, you can eat it. Okay. So what I'm going to do is I'm going to go through the next couple of slides, and then at the end I'm going to write them all on the board. So at the end you can take a picture of it or you can write it down as I go. Yes, ma'am.
When do you upload these videos?
The YouTube videos?
Yes.
We'll try and do it tonight.
Can you like try it, like really try it? Cause I'm like, I need
Yes,
this.
I will do it tonight.
Thank you.
Okay. Yes, I'll do it when I get home.
Do you edit a lot of stuff out?
No, I've tried it.
Please
No,
edit
I'm just
stuff out.
putting it. No, I'm just putting it online. I don't care. All right. So your first shape. Your first shape is linear. Linear is in a line. So if your compound makes the shape in a line, that is a linear shape. So linear is in a line. The example for that is CO2. The next shape is called trigonal planar. So trigonal means that you have 3 legs. The planar part means that if you put it flat on the table or the floor, like on a flat surface, it's going to lay flat like a plane. Okay, so trigonal planar, it's flat. Okay, trigonal planar is flat like a plane. Not a plane like an airplane, like a plane like P. I guess it's
Like in math.
like in math. Yes.
P-L-A-I-N, that one. Yeah, like a
No.
grassy plain, not a P-L-A-N-E.
No, it's still PLANE, isn't it?
No, P-L-N-A-E is the flying one.
The-
P-L-A-I-N-E. Wait.
No, that's like plain as in like plain vanilla or plain.
Huh? Yeah,
Like
the
boring.
plain. A P-L-A-I-N is a grassy plain. I promise you. You can look it up if you want. But just know I am 100% if I'm not 100%.
Okay.
That's wrong, it's not.
So your next shape, guys. Your next shape is tetrahedral. So tetrahedral, your prefix tetra means 4. So you have a central atom with 4 legs. So it can either be drawn like this, but there's a simpler way to draw it that you'll see. So I'll draw it on the board. So don't mind this one. Okay? So tetrahedral means you have one central atom with 4 legs. And then trigonal pyramidal. Trigonal pyramidal, again, trigonal because you have 3 legs. Now it's pyramidal because now it does not sit flat on a plane. Now it sits up like a pyramid. So if you notice, this central atom is kind of a little bit higher than your 3 legs. So it looks more like a pyramid. Right? Also, what I think it looks like is one of those back massagers, like that looks like the spiders that you got from the Cracker Barrel store. At least I did.
So we're gonna be making all these shapes out of marshmallows tomorrow?
Yes.
Yo, remember the Cracker Barrel board games we would play?
No.
Yeah, they do the peg jump. Oh my god.
All right, so your last shape is called bent, and your water molecule is your quintessential bent example. So usually if they're going to give you a question about the bent shape, it's going to be the water molecule. So bent is similar to your linear, so you still have 3 atoms, but instead of it being in a line, the 2 outer elements are kind of at an angle, and I'll show you why. Okay? So, to recap. Oh, my phone's right there. All right. So, let's see if I can do this by memory. So you have your shared atoms, your lone pair of electrons, your shape, and then your examples. Okay? So if you have, oh wait, my phone. If you have VF3 with 0 lone pairs, your shape is linear, and your example is CO2. If you have 4 shared atoms with no lone pairs, you have tetrahedral, and this is what your tetrahedral will look like. It looks like a cross or a plus sign. Okay, that's how you'll see it more often. This example is CH4. If you have, is it 5 or is it 4?
What's that one called? What's the second one
Oh,
called?
sorry. This is linear. This is tetrahedral. If you have, what is it? Trigonal planar.
Not the arrow.
Trigonal planar is
Trigonal pyramid.
this.
That's something like that.
That's none. That's 1, 2, 3, 4. Aha. Wait. This is 5. This should be 5. Sorry. That's 5. This is 4.
Oh, you just messed me up. I just put it.
I'm sorry. The example is
We're gonna take a picture of this, right?
Yeah.
BF3. And then trigonal pyramidal looks like this. No, that's 1. 1, 2, 3. This is trigonal pyramidal. It has 1. So you have 1, and you have 1, 2, 3, 4. So trigonal pyramidal is NH3.
No, that looks like, you know when you go super.
And then you have 1, 2, 3, 4 bent,
It's like a big octopus.
which looks
It's
like
a glowing head, and it looks exactly like that, actually. It's kind of
this.
scary, and it like throws an EMP out. Those things, I hate it. And then if you charge it,
2,
it's like a- I hate those.
3, and this is H2O. So, your lone pair of electrons, look what your lone pair of electrons are doing. So you have your trigonal planar. If you add in a lone pair of electrons, that lone pair of electrons are going to push all 3 of those legs as far down as it can. So then it makes it into trigonal pyramidal. So it looks like a pyramid. You have this lone pair of electrons influencing all the other ones. Your bent is going to also do the same thing, but now you have 2 lone pairs of electrons pushing down those 2 hydrogens. So these are the shapes you need to know. Those are the names, and then those are some examples. Bye, Anna. Have a good day. Any questions before you leave?